All right, hello and welcome. Today is May 4th, Star Wars Day. May the 4th be with you. Um, Welcome back. We already have a few people testing out our new emote. Yes, our emote has been approved by Twitch, so you can do integral of DL. You know, in life, you might take a bunch of little tiny L's, but eventually they add up to a big giant L. So that's what the new emote is. You'll learn more about it when you take your calculus class. It is Monday. We have lots of things to do before we can take our AP test. The tests will be next week, right? So we only have one last week for preparations. Now you guys are technically on Thursday, so you have a few extra days. This would have been AP week if everything was normal, but clearly it is not. Wow, okay, so today we will go over some of the FRQ questions from the MyAP that you had the option of doing. If you wanted to, I guess if you want to get a 5, you got to do everything, really. You got, let's see, I have pulled up Unit 1 and 2, so our focus will be Unit 1 and 2 today. And then over the course of the next several days, we'll try to get through all of them. Right. Finishing up grading all the quizzes, so we'll go over the quizzes as soon as we're done. We'll have more quizzes throughout. The optional one are the ones. Okay, everything else is optional. The only thing that is graded, so graded, MyAP MCQ, Canvas, quiz, plus final. So there you go. These are your graded assignments. They're in your assignments category in MyAP because when I unlock it, they turn into assignments. There's no way around it. There's no way to make it so that it's not in the assignments. All right. Here is Unit 1. The other ones. In question number 1, the question is a long free response question. Show your work, blah, blah, blah. All right, cylindrical object. So something is rolling down an incline. Don't know what the angle is. That's figure 1. It says a cylindrical object can roll down an incline as shown in figure 1. The incline is slightly less than 1 meter in length. A group of students wants to determine the acceleration of the object while it is rolling down the incline. The students have access to the following equipment: stopwatch, a clock, a meter stick, and a pair of calipers. Okay. Basically, it's small t, big L, small l. Ooh, can we get a sum of all small l's real quick? Oh, there we go. Sum of all l's. All right, assume the object moves with a constant acceleration as it rolls down the incline. Write an equation that includes acceleration and quantities that can be measured or obtained from measurements by using the available equipment in the list. All right. Let's see. Question is the acceleration g sine theta yay or nay? Yay or nay? Let's do a poll. I haven't done a poll in a while. The polls take kind of long to set up. Let me set up. Edit g sine theta a equals. So your options are vote yes for yes and no for no. All right. Is the poll active? The poll is active. So we are rolling down the ramp, Yikes, yikes-a-rooney. How many people do we have today? The numbers are increasing. People are waking up. It is a Monday after all. Yes. Kakarot moment indeed. Ooh, we got a no. Very good. We got more yeses. Interesting. You vote L's. That is quite an L. Quite an L. All right, I'm gonna close the poll. Polls. Blah blah blah. We have two no's. But we don't know. But we don't know the inertia. The inertia? How will you use inertia? Inertia is more of a descriptive property. How would you, I mean, you couldn't use that anyway. Are you trying to replace the word mass with inertia? Even though they're similar, they're definitely used differently in context. You can no longer vote. Oh, okay. Complete. Boom. And the answer is no. The answer is no. Why is it no? Why is it no? Well, we're rolling down the ramp. We're not sliding down the ramp, right? If we are sliding down the ramp, then yeah, we're definitely. You can't use inertia to find A. You need mass. Or do you? You don't, because there's no friction, and so the masses would cancel. But in any case, it is no because it is rolling and it is not sliding. If it's sliding down the ramp, then yeah, it's going to accelerate at g sine theta, which is much faster. It's rolling, so there's friction. Ooh, interesting. A cylindrical object can, yeah. It is rolling because there's friction. There's static friction, if you will. There's static friction. It is not skidding, so there's no kinetic friction that is actually slowing it down, but the static friction is forcing it to turn. Now, as you go, as it picks up speed, it'll go faster and faster, which is really cool. Well, let us get to the question. It says, assume the object moves with a constant acceleration as it rolls down the incline. Write an equation that includes acceleration and quantities that can be measured or obtained from measurements by using the available equipment in the list. Ooh. All right, so basically, which kinematics equation can you use? So here's part A. We have some options, right? But we want to make sure we choose the best one. Now, Mikey doesn't even have, or sorry, Raph doesn't have acceleration in it. So the choices are Mikey, Leo, and Don. So Don is and Leo. Okay, so these are our options that have acceleration in it. Which one is the best? Well, based on the equipment that we have, which is stopwatch, clock, meter stick, and calipers, notice how we cannot directly measure our instantaneous velocities. Okay, what can we use to find instantaneous velocity? What would we need for instantaneous velocity? Well, we would need a photo gate or something else like a motion sensor. So we don't have that. Now we want to simplify as much as we can. Of course, we can set our initial velocity to be 0. And that gets rid of some terms. And so d is equal to 1/2 at squared. Yeah. Oh, I just lost like half the class. What happened? Did I disconnect? Well, they just didn't like it and just left. Did people just rage quit? Probably. Yeah, so let's go and use Donatello. Donatello would be the best because we can actually measure D, and we can actually measure T, and then figure out what A is. Yeah. Well, not everyone wants to pass, I guess. Part B, let's go to part B. Design an experimental procedure the students could use to measure the quantities required to determine the acceleration of the object. So here they actually made a chart, and then later on you actually have to write about it, like procedures in your labs. It is very important that you incorporate the instrument into your procedures. Right? So don't just say measure D. Use a meter stick to measure D. Definitely not a caliper, because caliper's too small. Okay, so let's see. What do we need to measure? Well, we need to measure. We definitely D. So D, which is displacement. Displacement D, and we're going to use the meter stick to do it. Oops. Well, that didn't work. Meter stick. We also need time. We'll use the stopwatch. Okay, that should be good to go. Should we make a chart too on the AP exam, or just mention the equipment? If you're very descriptive in your explanation, technically you don't really need a chart. They actually gave you a chart in this question, so then yeah, you have to fill in the chart. Charts for procedures is not mandatory. Describe the overall procedure. So now you have to write it. So step 1, measure the displacement. Now we can measure it from front to front, or center of mass to center of mass, I suppose. Now that's going to be based on how you stop the clock. So if you do it from center of mass, then you would need to wait for the center of mass to cross the finish line. So it also says this part is kind of important. Provide enough detail so that another student. Oh, okay, not that part. Where's the other part? Oh yes. Include any steps necessary to reduce experimental uncertainty. Okay, so what does that mean? What are they trying to say here? Include any steps necessary to reduce experimental uncertainty. Well, we want to make sure we do everything efficiently, and most importantly, we want to minimize the sources of error. Minimize the sources of error. So So how you let go of multiple trials? Yeah, that's another good. That's a very important step. So typically at the near the end of your procedure step, do multiple trials, or don't just say multiple trials. Say like take 5 trials or something. Actually, what you're writing, procedure steps that another student can follow. So don't just tell them to do it. Do it a bunch of times, but tell them a specific number. It might help. 5 is a pretty good number. Take 5 trials. Take 5 trials. Definitely. Now, how you do the lab is also important. There are ways to minimize sources of error. Perhaps, let's say you have your ramp and your cylinder here. If you recall, when I did the marble races, when I had a ramp with four different railings, one's like something like this, the other's like drops very carefully. I don't know, I can't remember. There's a brachistochrome or something. Yeah, remember how we did those marble races? Now I used my meter stick kind of as a guardrail, so I kept the objects from sliding down. So use the meter stick as a boundary, as a guardrail, to hold the cylinder in place, and then lift up the meter stick at t equals 0 to allow the cylinder to roll down. So those are like minor details that kind of differentiate a 5 from a 4. Like a 9 essay versus an 8 essay. What quantities could be graphed to yield a straight line that could be used to determine the acceleration of the object? Okay, the only way to get acceleration from a straight line is to take the derivative of your velocity time graph. So if you have a velocity time graph, you can find the slope. So vertical axis has to be y, horizontal axis has to be time t. Now the problem is we have to figure out how to get v. Strategically, we can set VO to be 0, but we need to figure out some sort of v final. Okay, there is a way to do that, and that would be Raphael. Okay, so with Raphael, we can get the average velocity, and the average velocity, of course, is v initial plus v final over 2. That's the average of two numbers, and therefore you can set this to 0, which would give you v final over 2. Okay. And then you would have to kind of explain that method. How could the graph be used to analyze? Well, acceleration is the slope of your velocity time graph, so slope equals your acceleration, etc. Or use the definition of acceleration dv dt. I should say delta v delta t over delta t. Right. Let's see. After rolling down the incline, the cylindrical object rolls across a horizontal surface as shown. The object hits a wall and then bounces with the same speed it had before hitting the wall. So what kind of collision is this? Well, if it's coming back at the same speed, it must be conserving everything. Note that during the bounce, the object is in contact with the wall for a time interval that is very small, but not 0. Yeah, if we're coming back at the same speed, of course we are going elastic. Yeah, both momentum and kinetic energy is conserved. Okay, so it says on the dot below which represents the object during the time it is in contact with the wall. Draw an arrow showing the direction of the object's acceleration. So during the collision, which way is the acceleration? That's the question. Of course, the wall is not only stopping the object, but also changing the direction of velocity, sending it the other way. So the initial velocity was to the right, the final velocity is to the left, then the acceleration must be to the left. Okay, this is not an FBD, it's a acceleration vector. During the time the object is in contact with the wall, is the magnitude of the acceleration greater than, less than, or the same as it was while it was rolling down the ramp? Ooh, this is interesting, and we have to explain our reasoning too. Okay, so now we have to take a look. All right, so when we're coming down the ramp, what is our acceleration? Well, our acceleration by definition is delta v over delta t. Okay, and how did my acceleration change? Well, let's see. We'll call this one acceleration 1. We'll call this one acceleration 2, the one where it reverses directions. I should put it over here. Acceleration 1 was from 0 velocity to v velocity in delta t amount of time. Right? So acceleration 1, this is the general formula. Acceleration 1 must be equal to final minus initial. So v minus 0 is v divided by delta t. Okay, what is acceleration 2? Well, acceleration 2, well, the velocity is changing direction. It goes to the right and then to the left. Right, and we're comparing the magnitudes, of course. Oh no, what happened? I got logged out. Oh, I didn't hit stay logged in. That is quite unfortunate. Okay, we are back logged in. Okay, so acceleration 2 would be negative v minus v over not the same delta t, but a very short amount of time, t. And so we have, 2v over t. Now this one is big, this one is tiny. And so with a small tiny time and a big velocity change, of course your acceleration would be much more when it's crashing into the wall. Let's see, MyAP. There we go. Trying to get back to the page. FRQ. Oops. It's not what I want to do. There we are. Whoa, this is not. Oh man. Oh, that's unit 7. Sorry. I hate how the auto logout feature works. That's quite unfortunate. Okay, so ways to justify. Well, the change in velocity is much greater when you're changing the direction during the collision. And furthermore, since the time is much smaller, of course you're going to have a bigger acceleration, magnitude of acceleration on the object during the collision. All right, so that's number 1. Let's take a look at number 2. Wow, that took way too long. We still have a bunch other to do. Now, let's see if we can do this one slightly faster. Here's question 2, unit 1-2. We have an astronaut, and the astronaut's tossing a ball. Oh, it's a classic free fall problem, but we're on planet X. An astronaut holds a rock 100 meters above the surface. The rock is thrown at 15 meters per second, blah, blah, blah. The atmosphere of planet X has a negligible effect on the rock, so there's no air resistance. We're just in free fall. Okay, determine the acceleration due to gravity of the rock when it is on planet X. So we don't actually have planetary data. We're not using the gravity equation. We are finding the acceleration due to gravity by finding acceleration using VOVAT. So let's see how we can find acceleration using VOVAT. We are tossing the object, so v initial is equal to 15 meters per second. V final is unknown. That's the the final velocity right before it hits, the ground. The acceleration is some sort of negative g. Well, it's some other g, not 9.8. We're on planet X, so we don't know what it is. Displacement. Well, displacement, this is the change in position. We started up here at 100 meters. We are now down here at 0 meters. Final minus initial, 0 minus 100. That gives me negative 100. And time is 10 seconds. Wow, we have so many things. 1, 2, 3. We're looking for this one. An equation with acceleration, blah, blah, blah. Well, I guess Donatello. Solving for A, so that's D minus VOT times 2 divided by T. Equals A. Okay, so isolate and then solve, right? What is this value? We need to know so that we can continue the rest of the problem, so that we can compare this to Earth and stuff. So that's 2 times 100, negative 100. My computer is dying. Let's plug it in. Yay. All right. Negative 100 minus 15 times 10, so 150, divided by 10. So that gives me negative 250 times 2 is 500 over 10 is 50. Wait, what? Really? That's a lot. Is that right? Did I? Oh, I forgot the t squared. Very good. T squared. So that's 100. That makes more sense. 5. Yep. 5 meters per second squared. T squared. Oh, right here. VOT plus 1/2 AT squared. Yeah, 50 G's is quite a lot. We'd probably faint. It'd be so much that the blood would accelerate downwards to our feet, and our heart would not be strong enough to pump the blood into our brains, so our brains would suffocate, and basically we would faint. All right, cool stuff. Oh, I mean, even standing up would be very difficult. You would feel 50 times heavier, so you'd be crawling onto the ground, or like holding onto the floor. Standing up would be too difficult. So now we know that it is definitely less than Earth. So G star is positive 5 meters per second squared. Let's go back. We're supposed to do this faster, but it's not happening. How does the speed of the rock when it reaches the ground, Vd, compare to the speed of the rock when it is thrown upwards? Ah, classic. So we are comparing the initial velocity to the final velocity. Of course, it creates a parabola. Now, if you throw it straight up, it's still a parabola. The parabola happens in the space-time graph instead of the space graph. So I'm drawing the parabola in the y versus t graph. Of course, when you go upwards at 15, by the time you come back to the same height as the cliff, you're going to go downwards at 15. And so you're starting with a negative 15 meters per second, and you're going to accelerate for 100 meters worth of distance. Of course, since you have time to accelerate, you're going to go faster. Faster, faster, faster. A student wants to know how the motion of the rock would be different if it was thrown upward at 15, blah, 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 on Earth. Ooh. Explain how the motion of this would be different on Earth. So we have to compare maximum height, the speed at which it reaches the ground, the time, it, and the total time. So a problem that involves everything. I wish the test had a kinematics question. We'd have 100% pass rate. So we want maximum height. We also want final velocity, and we want total time. Right. Okay, so how do I find maximum height? Well, we recall that at the top of your trajectory, the velocity is equal to 0. You know, it's changing direction, it reached a maximum, blah, blah, blah. You can figure out how long it takes, and then technically you could divide it into 2 parts. You can, you know, have part 1 where you're going up, and then part 2 is a free fall problem going down after you find maximum height, of course. Oops, there we go. So velocity at the top is 0, and you can use that to find height. Or you could just answer it conceptually. We know that gravity on Earth would be 9.8, which is more. So when you throw something upwards at 15 meters per second, and you have a higher gravitational pull downwards, so velocity is 15 with the acceleration being downwards at negative 9.8 versus negative 5. Okay, so if you're accelerating downwards at a higher rate, of course you're going to slow down at a in a shorter amount of time. Therefore, you don't go as high. So height on Earth is definitely less. What else? Speed at which it reaches the ground. Okay, so now even though we don't go as high, this part is true in that when I get back to the edge of the cliff, when it goes up to the max height and then back down again, it's still a parabola. Therefore, since I launched it at 15, whether it's on Jupiter or Earth doesn't matter, when it comes back, it'll be symmetric. Therefore, it'll go downwards at 15 meters per second. Right? But now we are accelerating downwards 100 meters, starting with the same speed, but with 9.8 instead of 5. So if I have a downwards velocity and I'm accelerating downwards with a greater acceleration, of course we would reach a faster velocity at the end. Total time in the air, how long? Well, is there an equation we can use to find time? Well, there are a couple. Yeah, technically you could use Raphael. Raphael tells you that d over v bar is equal to t, and v bar on Earth, is it greater than or less than or equal to v bar on planet X? Well, final minus initial. Oh, it's final plus initial over 2. At least we're just comparing magnitudes. Okay. Since on Earth we're reaching a greater velocity at the end, we're starting at the same speed, 15. And of course, the average velocity on Earth would be bigger than the average velocity on planet X. Therefore, it takes less time on Earth. All right, that did take less time. That's good. Let's go to Unit 2. That is not unit 2. Unit 2. All right, so first one, a dynamics problem. Okay, so we got 3 blocks, blah, blah, blah. Block 1 is resting on the floor with block 2 on top of it. Block 3 is on the table, negligible friction by a string over a pulley, and string and pulley have no mass. Why is that important? String and pulley have no mass. Massless stuff. Well, this is an ideal situation. And when it's ideal, what can we ignore? We don't have to worry about rotational dynamics. Very good. So moment of inertia of our pulley is 0. Remember, if it was a disk, it would be half m r squared, but m is 0, so it's 0. Not only that, the tension forces are the same on both sides of the pulley. The pulley is merely changing the direction of the force. All right, let's answer the questions. Let's see. On the dot that represents block 1, draw and label the forces, not the components. Each force must be represented by a distinct arrow starting and pointing away from the dot. Draw relative lengths, blah, blah, blah. Okay, so number 1 is on the floor. So we got to do an FBD. So of course number 1 has, and this FBD is straight from the center of mass. Since we know it's not rotating, they're just having you draw all the forces from the center of mass. If it was rotating, you want to draw the forces where they are applied on the body. So of course we have M1G down, or you can also call it F1G, or FG1 I should say. We also have the force on number 1 by number 2, F1-2. Okay, and then oops, I have to do it relative length, so let me make it shorter. Oh, great. Well, starting all over. So here's M1G, and I'll make F1-2 shorter, because I know that the mass of number 2 is smaller, or it's a smaller box. And then we have the normal force from the ground, and the normal force from the ground should be bigger. And we should label them. Don't just call it FN, because they're, especially when there are multiple objects, label them with their number. On the dot that represents block 2, draw and label force. All right, FBD for number 2. FBD for number 2. Well, number 2 is being pushed up by number 1, and that is the normal force. This is the normal force for number 2. Right. And of course gravity pulls it down. Now the force that number 2 applies onto number 1 is the weight of the object. Where's M2G? Okay. Now, is there a tension? Is there a tension force pulling it up? Chat, is there a tension force pulling block 2 up? Not yet is the answer. Not yet. Yeah, we're all at static equilibrium right now, so nothing is accelerating. Therefore, nope is the answer. And that is true because there's no friction. There's no friction. If there was static friction on the table, then it is possible to have some sort of tension. Is there? Well, I could technically pull block 3 to the left a little bit so that it is touching block 2 is touching block 1, but the entire magnitude of the weight is not applied onto block 1. Right? I could do it such that, you know, it's just on the surface, it's skimming the surface, but it's not quite. It's kind of like holding a book, but someone else is pulling on the book slightly upwards. Even though the object is not accelerating, you are doing, you know, less holding, or you're doing less work holding up the book because you're getting help. All right. Consider this. Okay, block 1 is removed without disturbing block 2. So it's like playing Jenga, and you just removed block 1. Now block 2 is going to accelerate, especially because there's no friction on the table. Consider the scenario without using equations. Without using equations. Make a claim about the motion of block 3 in terms of balanced or unbalanced forces. Well, since there is no friction on the table. Wait, was that stated? I keep saying that. Oh yeah, smooth table with negligible friction. Yes, so there's no friction. Then there's only one force on the x-axis for the third block, which is pointed to the right, the tension force. So we could say that there's an unbalance in the force. Ooh, Star Wars Day. There's an unbalance in the force, which accelerates us to the right in the x-axis. But in the y-axis, the force is balanced. The normal force for block 3 cancels out the weight of block 3. But because there's an unbalance in the force in the x-axis, it's going to accelerate in the x-axis. Derive an equation for the acceleration of block 3. So now we have to actually do stuff. Let's see. So here's block 3. Block 3 is being pulled to the right with tension force. There's Fn3 up. There's M3G down. We can say sigma Fx is equal to the tension force, which is equal to mass 3 times acceleration. And we can find the tension force from the other one. Let's see. Tension force up, M2G down, and in the y-axis. Now this one's going downward, so tension up minus M2G equals negative M2A. If you don't want to do this, the negative sign, you could always look at it sideways. Remember, instead of looking at it in the curved space model, you can look at the flat space model. Oh look, the world is flat. Whoa. In the flat space model, object 3 doesn't change. But object 2 looks different. Object 2 is being pulled to the right with gravity, by gravity I should say, and it's being pulled to the left via tension. And so you have M2G minus Ft equals M2A, and this gives you the same thing. All right, so we have M2G minus M2A equals M3A, and then isolate and solve, or just sigma F over sigma M. Acceleration is equal to the net force on the system, which is M2G, divided by the sum of the masses. Yeah. Flat space model. The Earth is flat. Whoa. It is flat in small patches. In small patches. Your little tiny ds vector, or the ds, the arc length, gets flatter and flatter as you shrink in size. Derive an equation for the acceleration. Oh, we just did that. Describe in what ways your answer to part B2 is or is not consistent with your claim in part BI? Okay, well, it is consistent in that the net force on object 3 is the tension force, and the tension force is purely based on the acceleration of object 3. Now, what we need to incorporate is the fact that the acceleration of object 3 is still dependent on the overall mass of the system. Curve becomes line, indeed. And so that part is, was not in our explanation in BI. So that's something I would add in in C. Okay. Graphs on the axes below. Sketch graphs of the velocity and the acceleration of block 2. Block 2 is the one that is falling down. Block 2 is the one that's falling down. So we have velocity of acceleration. Okay. Now the acceleration of block 2 is actually negative, nice and constant. So it's a constant negative number. Negative value. And therefore this means that the slope of velocity is a constant negative slope. Starting from 0 velocity, we have a constant negative slope. Okay, is that it? And that is all. Cool. And then the last question, Unit 2-2. Do all the units have 2 exact FRQs, or are there more or less? Someone who actually did it, please answer the question. Oops. Whoa. Okay. This question is short. Okay. Blah, blah, blah. Oh, we have 2 objects. Let's see. Object A are on a horizontal surface. The friction is negligible. Nice. A is moving to the right. B is at rest, and they're about to collide. This is a center of mass problem. Interesting. Okay. Let's see. On each of the dots, which represents the blocks while they are in contact. So the moment they collide, draw a single arrow to indicate the direction of the net force, if any, exerted on each block. So the net force on each block. Okay, so during the collision, let's see, block. Well, there's an impact force. And so the impact force on block A, are these considered long or short FRQs? I see. Did you see that? This question is a short for your response question. So these are all 15-minute questions. Block A is stopping, so the impact force is this way. The other one, Newton's third law kicks in, opposite equal reactionary force. So it's that way. During the time that the blocks are in contact, describe whether the center of mass of the 2 block system is speeding up, slowing down, or staying the same. During the time that the blocks are in contact. So we want to talk about the center of mass. The center of mass. Well, let's see. Is momentum conserved? Is momentum conserved in this thing? Well, during this collision, momentum is conserved if there's no external force. Well, I asked that before. Oh. Momentum is conserved. Oops. Conserved. If there's no external force, no external force. The impact force is an internal force. And so no external force, then center of mass stays the same. So whatever it was doing now stays the same can mean two things. It's basically Newton's first law in that object in motion stays in motion, object at rest stays at rest. So I should write if at rest stays at, okay, this is not very helpful. I'll just write stays the same, Newton's first law. We can't see the screen. Oh, great. P is conserved, no external force, center of mass stays the same, which means Newton's first law. Now you have to determine if it was moving with constant velocity, or was it at rest initially? Okay. One way to figure out what the velocity of the center of mass is to look at the momentum of the object, or of the system, I should say. So notice how A is moving with velocity v, B is stationary. Okay. Now, of course, the center of mass, the location of the center of mass is currently in the middle, assuming that the blocks are equal in masses. So the fulcrum or the pivot point is directly in the middle. This is xcm. But how do I find VCM? Okay. If you recall the XCM formula, XCM is M1x1 plus M2x2 dot 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 over M1 plus M2 dot dot dot. One could say this is XCM is equal to M1x1 plus M2 x2 dot 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 over mass of the system. So this is m sys times xcm is equal to m1 plus m1 x1 plus m2 x2 dot dot dot. And so if I just divide both sides by delta t, okay, I get m sys times velocity of the center of mass is equal to m1 v1 plus m2 v2 dot, dot, dot. It's the momentum. It's almost like a PIC collision. Now this is not a collision, of course. It's just telling you how to find the velocity of the center of mass. Of course, initially the velocity of center of mass is not zero. Therefore, it did have something. The velocity of center of mass initially is equal to m1 VO, VO being the velocity of object A. I should call this A. Mass of object A times velocity of object A over MA plus MB, which is some sort of positive value. So the velocity of the center of mass was to the right. And so after the collision, it's also going to be to the right. But the question itself, is it speeding up or slowing down? Well, it's going to stay the same. It's going to go at the same velocity. It's just because the momentum is conserved, there's no external forces, then it cannot be speeding up. It's not going to accelerate. Oh, now it's different. Whoa, we have an incline now. What's different about inclines? Well, with an incline, we now have gravity. Whoa. Of angle is 37 degrees. which is about 60%. Now mg is down, of course, normal force is up. The vector component that is accelerating the object is mg sine theta. Okay, mg sine theta. Similarly, for the other object, it is also downwards. Now the blocks are the same, so I'll just use the same color, blue, which is also mg sine theta. Theta being the angle at the top. All right, so let's see. The surface is tilted. Okay, each block has a mass of 0.2. Calculate the magnitude of the net force exerted on the two block system at the instant shown. Okay, the net force must be the forces that are unbalanced. Of course, the y-axis, is this way, the x-axis is this way, and so mg sine theta plus mg sine theta, or 2 mg sine theta, which is in the x-axis. So sigma fx cis for the system, because there's no friction. At the instant shown in figure 3, the blocks are moving towards each other. Okay, at 0.35, the blocks collide 0.5 seconds later. What is the speed of the two-block system? Two-block system center of mass just before the blocks collide. All right, so okay, so this one's moving this way, and this one's moving that way, and then they collide 0.5 seconds later. All right, what we could do is find, again, use the center of mass formula. So the velocity of the center of mass, and we want to do it after the collision. So there would be basically mass of the system times velocity of the center of mass is equal to the final momentum of the system. So we'll call this F. And the final momentum of the system must be equal to, now you don't have to use momentum, even though this is a dynamics unit. Of course you can use dynamics. I'm just using momentum because it's much faster. When you're taking the AP test, the questions aren't from just one unit or two unit or another unit. They'll be combined. So you can use any physics knowledge as long as it's applicable in the question. This is P1 final plus P2 final. So VCM F is equal to that divided by mass of the system. This would be mass 1 times velocity 1 final plus mass 2 times velocity 2 final divided by mass of the system. Now to find the final velocities of each object, V1 final is equal to V1 initial plus acceleration times time. And we know what acceleration is. Acceleration is equal to g sine theta. These blocks are sliding. And time is 0.5 seconds. V2 final would be V2 initial plus acceleration times time. The acceleration is the same for both. The time is the same for both. What is different is the initial velocities. V1 initial is going to the right, right? You want to tilt your head. X is positive going down the ramp. So V1 initial is positive 0.35 meters per second. And V2 initial would be negative 0.35 meters per second. And that should be it. All right, that is, I guess that's it. We should continue to work on your MyAP questions. Should we have a quiz tomorrow? No, I think I'm going to do, we're going to do Unit 3 and 4 tomorrow for the FRQs, and then we'll have a quiz on Thursday. All right, thanks for tuning in. I'll see you next time.